This video is an introduction to chemical reactions. We're going to start off coming up with a definition of a chemical reaction without using the word chemical or the word reaction. And this definition isn't too bad. A chemical reaction is a process in which one or more substances form one or more new substances. The substances you start off with in a chemical reaction are called reactants. And the substances that you end up with in a chemical reaction are called products. And every time that we write chemical reactions, we always write them with the reactants on the left, an arrow, and then products listed on the right. Now, the next question that we need to ask ourselves is, how do we know that a chemical reaction has occurred? And there are lots of different signs that we can see and that we can determine that a chemical reaction has occurred just by observing a beaker or a flask or anything like that. And the first one is a bubbles or gas formation. And I want you to be careful with these because sometimes the change of boiling is a phase change, and that's a chemical change. It's not a chemical reaction. There's no reaction that's happening there. But we do have reactions that do make gases. So just because you see bubbles forming doesn't mean that there is a reaction that's happening, but it can be an indication that a reaction has occurred. Another indication is a color change, and we see this in the fall when the leaves change from a green to oranges or reds. That is the breakdown of the chlorophyll in the leaves, and that's causing the leaves to change color, and that is a chemical reaction. Again, a color change in and of itself does not necessarily guarantee that a reaction has happened, but it can be a good indication. Another thing that can happen is that light can be given off when we have a chemical reaction occurring. You can see that with something like fireworks. When we burn the various metals that are found in fireworks, they give off different colors of light. Another indication can be a temperature change. If the beaker starts to heat up or if it starts to feel cold. The little heat factories, the little heat packs that you put in your gloves when it gets cold outside, that is a chemical reaction that's occurring in those little packets. And the last one, although this isn't an exhaustive list, but these are the most common indications, is the formation of what we call a precipitate. And what a precipitate is a solid that is formed when we mix two solutions together. And you'll see, like in the beaker, it's a yellowish color, and that is a precipitate that is formed, and that's another indication that a reaction has occurred. One thing that I will say is that if you see two or more of these things happening, you can be pretty sure that it is a chemical reaction. If you just see one thing happen, again, it could be an indication, but it's not a guarantee. But the more of these things that you see occurring, the stronger the indication is that there has a chemical reaction has occurred. And one way that we write out chemical reactions is to write it in what we call a chemical equation. And there are different ways to write these chemical equations, and the rest of this presentation we're going to spend focusing on these different ways. And the reaction that we're going to use, that we're going to focus, is the reaction between sulfuric acid and sodium hydroxide. We're going to start with word equations. And word equations simply write out the reaction in words. And typically, when I ask you to write out an equation in words, you're starting with a chemical formula. But in this case, we're just going to start with the word equation. You've got to start somewhere, so we're going to start with word equations. So the first thing that you do is you write out your first reactant, which in this case would be sulfuric acid. There are different words that we can use when we see the plus sign. Some of the common ones are combines with, reacts with, and, plus. There are probably some other ones out there, but those are probably the four most common words that we use when we have a plus sign on the reactant side. And then we say the other reactant, which in this case would be sodium hydroxide. The arrow that we use is called the yield sign. We don't use an equal sign. Equal signs are used for numbers. And so we use an arrow or a yield sign because we are talking about substances. And that arrow, you can say it yields, it makes, it produces, it forms. We don't say that they are equal to each other, though. They make other substances. And then we write our first product, which happens to be sodium sulfate in this particular example. Now on the product side, the plus sign, we usually don't have very many words that we use for the plus sign. We usually just are limited with and plus. That's just usually the way that it works. That's just what most people say. And then at the end, then you're going to list the last substance, which in our case would be water. And so if we were going to form this into a sentence, the sentence would look something like sulfuric acid reacts with sodium hydroxide to produce sodium sulfate and water. Now the next kind of equation that we're going to use, depending on what source you look at, sometimes it's called a formula equation and sometimes it's called a skeleton equation. You'll probably hear me refer to them more often as skeleton equations versus formula equations, but I will use both words somewhat interchangeably. And what we do there with the skeleton equations is that you're seeing us starting to use chemical formulas in place of the words. So what you would need is you would need to know what the formula for sulfuric acid is, and I hope that you guys all know that sulfuric acid is H2SO4. It reacts with, so we use a plus sign there. The next substance is sodium hydroxide. That formula is NaOH. To produce is an arrow. Sodium sulfate is Na2SO4. Remember that the sulfate ion has a -2 charge and the sodium ion has a +1 charge, so we need 2 sodium ions for every sulfate ion. Then we have a plus sign for the word and. And we end this equation with water, which is H2O. And so our skeleton equation would be written out as H2SO4 plus NaOH, arrow, Na2SO4 plus H2O. And that would be your skeleton equation. The next kind of equation that we're going to talk about is a balanced chemical equation. And the balanced chemical equation is based on the law of conservation of matter, which states that matter cannot be created or destroyed, which means that the numbers of atoms of each element in the reactants, they must absolutely equal the number of atoms of each element in the products. I cannot conjure a sodium atom out of thin air. If I'm going to have a sodium atom in my products, I must have a sodium atom in my reactants. Now, in order to get these to balance out, we're going to use coefficients to get them to balance because our subscripts are used to balance our charges, so we can't touch those, but we can use coefficients to balance out these numbers of atoms. And so the method that I use to balance a chemical equation is called, I call it the scoreboard method. And I'm just going to show this to you briefly. I'm going to quickly balance this equation, but in class we're going to spend much more time working on balancing chemical equations. So if you're not quite following this, don't worry about that because we're going to spend a lot more time in class balancing chemical equations. But the way scoreboard starts is I list either each atom or sometimes in class I'll show you that I will use polyatomic ions also. But in this case, I'm just going to stick with elements, list the individual elements. Depending on where you look, some places like to list the elements for the reactants and for the products. I prefer to list them right under the arrow. So that way you don't have to write them down twice. And I just think it's just easier to keep track of things if I just write it down once than have it have two different columns for my atoms. And so what we're going to do is we need to figure out how many atoms of each element we have on each side of the chemical equation. And so let's start with hydrogen. And we have 2 hydrogen atoms in our sulfuric acid, and we have 1 hydrogen atom in our sodium hydroxide. So that gives us 3 hydrogen atoms for our reactants. And in our products, we have 2 hydrogen atoms found in the water molecule. The next element that I listed was sulfur, and I have 1 sulfur atom in my sulfuric acid in my reactants, And in my products, I also have one sulfur atom for my sodium sulfate. Oxygen is found in every substance in our reaction, and I will tell you that's not necessarily an unusual thing. Oxygen is found in lots and lots and lots of compounds, so just be aware of that and keep an eye open for oxygen, because oxygen and hydrogen are the two little sneaky guys that end up in almost every compound. So we have 4 oxygens in our sulfuric acid and 1 oxygen in our sodium hydroxide for a total of 5 oxygen atoms for our reactants. And we have 4 oxygen atoms in our sodium sulfate and 1 oxygen atom in our water to also give us 5 oxygen atoms for our products. And finally, the last element that we're going to put on our scoreboard is our sodium atoms, and we have 1 sodium for our reactants and 2 sodium atoms for our products. Now, for this chemical reaction to be properly balanced, every single number on the right or on the left for each element needs to be the same on the right. So I should have the same number of hydrogen atoms, same number of sulfur atoms, same number of oxygen atoms, and the same number of sodium atoms. And as you can see, I don't have that. And if you remember that I mentioned before, oxygen and hydrogen are found in lots of different substances. So here's a little tip, is when you're balancing these chemical equations, you balance your oxygen and your hydrogen last. So, knowing that, let's look at our sodium, because we want to save oxygen and hydrogen for last. So our sodium is not balanced. We have 2 on our reactants, one on our reactant side and 2 on our product side. And so the way that we're going to do that is we're going to put a 2 in front of the sodium hydroxide, and that balances our sodium. But there's oxygen and hydrogen found in sodium hydroxide, so you need to make sure that you haven't gotten oxygen and out of balance. And so what's happened here is we have 4 oxygens still from the sulfuric acid, but because we now have 2 sodium hydroxides, we have 2 oxygen atoms from the 2 sodium hydroxides that we have. So then we will have 4 plus 2, and that will give us a total of 6 oxygens. It also changes the number of our hydrogens. We still have the 2 from our sulfuric acid, but now we have 2 more hydrogen from the sodium hydroxide for a total of 4 hydrogen atoms. If we put a 2 then in front of our water molecule, then because that's the only place that hydrogen is, now we'll have 2 water molecules, and that gives us a total of 4 hydrogen atoms. And then we need to add up our oxygens. Again, we have 4 from our sodium sulfate, but now we have 2 water molecules, and that gives us 2 oxygen atoms. So 4 plus 2 will give us 6. And that is your balanced chemical equation. That's how we balance them. But again, if you didn't quite follow that, I will show you lots and lots of tips and tricks in class. We're going to get lots and lots of practice balancing chemical equations. So don't worry about that too much. I just wanted to make you aware of one way to write out chemical reactions. The last way that we're going to talk about is a complete chemical equation. And this one, I'm going to just kind of gloss over a little bit, but later on this unit we will spend more time learning when to use these symbols, and we'll get lots of practice writing complete chemical equations too. So this is just a really quick overview. But a complete chemical equation uses symbols to show what phase or state of matter a particular substance is in a chemical reaction. And you will see four symbols that we use. The first one is an S in parentheses, and that stands for solid. We have L in parentheses, that stands for liquid. We have G in parentheses that stand for gas. And the last one you guys have seen on some of the naming quizzes, and I've kind of briefly talked about it, is the symbol AQ, and that stands for aqueous, meaning that it's been dissolved in water. And so we will go back to our balanced equation, and you look at each substance and you determine what phase of matter this is in. And I know when you start off, this can get a little confusing, and you might not be sure about this. But again, we're going to spend time on this, so I'm just going to show you kind of what this looks like, and then I'll show you how you can tell what phase each substance is in. All right. So sulfuric acid, because it is an acid, it's dissolved in water and it is aqueous. The next one is sodium hydroxide. And while sodium hydroxide can be dissolved in water and therefore it could be listed as AQ, for this particular example, we're going to pretend that we actually have sodium hydroxide pellets. And that is how you purchase sodium hydroxide. You purchase it in little round pellets, and then you can make your sodium hydroxide solution as concentrated as you need it to be. But for this particular chemical reaction, we're just going to decide that the sodium hydroxide is a solid, so you would use an S. The next substance would be AQ. It would be dissolved in water because you have your sulfuric acid already based in water. So now your chemical reaction, everything is happening in a bunch of water, even though you've dropped solid sodium hydroxide pellets into your beaker or whatever it is that you're using. You might be doing this in a test tube. But sodium sulfate would be aqueous. It will dissolve in water. And our last substance is water. Which is a liquid. We don't write water as AQ because then water would be dissolved in itself, and that doesn't really make a lot of sense. So water would be a liquid. And so your complete chemical equation, your complete balanced chemical equation would be H2SO4, AQ, plus 2 NaOH, S, yields Na2SO4, AQ, plus 2 water molecules as liquids. And that is all that I have for you guys. I hope that this has made a lot of sense and will help you be prepared for the upcoming unit.